Hi everyone, welcome to meeting 9. In this meeting, we're going to talk about RSA restrictions and some related topics. And we're going to run RSA on text documents. So here are the restrictions for RSA. P and Q must be large prime numbers to make it safe. Also, it's not only safety, but if it's too small, then it won't work. C and M are both smaller than N. C is the ciphertext and M is the plaintext. So both the ciphertext and the plaintext need to be smaller than N, or else it doesn't work. For public key E has to be an integer between 1 and phi n, and E is coprime with phi n, which means that the only common factor of E and phi n is 1. For private key D has to be bigger than 0, and D times E divided by phi n has a remainder of 1. So these are the restrictions. For the first one, P and Q are large prime numbers. The topic that we are going to cover about this in the future is prime factorization to find P and Q. We're going to create a code to prime factorize numbers that we input. On the right, this is a big N, and this is the corresponding P and Q. So this is the largest N that humans have been able to prime factorize. So as long as the P and Q are bigger than these two numbers, then theoretically no one can prime factorize it, and the encryption will be really safe. C is less than N and M is less than N. So because the ciphertext C is the remainder of M to the power of E divided by N, so C must be smaller than N. Similarly, because the plaintext M is the remainder of C to the power of D divided by N, so M must be smaller than N too. To ensure all letters and symbols Unicode character sets are available, N must be a big number, because the letters and symbols, their Unicode character sets are all 4-digit numbers. So to be safe, we want to make N at least 5 digits. So for example, we have the public key E is 3, private key D is 7, M the message is 13, and N is 33. In this example, phi n equals phi 33, because we know phi n, when P and Q are both prime numbers, it will be equal P minus 1 times Q minus 1. So if we prime factorize 33, it equals 3 times 11. So phi 33 equals 3 minus 1 times 11 minus 1, which is 2 times 10, which is 20. So we know phi n equals 20 in this scenario. E times D mod phi n should equal 1. So E times D, which is 3 times 7, which is 21, mod 20 equals 1. Mod just means 21 divided by 20, and the remainder, so it's 1. Let's look at the code. This is the code for experimenting with the value of n. So at the front, it's the same as before. We have an encryption function and a decryption function. In the encryption function, we take in P, Q, E, and M, find n, which is P times Q, find C, which is M to the power of E mod n, which is M to the power of E divided by n's remainder, and then return C, which is the ciphertext. For decryption, we use P, Q, D, and C. N equals P times Q. and then m equals the remainder of c to the power of d divided by n. And lastly, we return m, which is the plaintext. Here, the three restraints are d is greater than 0, p times q is greater than m and is greater than c. E and phi p times q are coprime. So now we are going to experiment with the value of m because we know that m has to be smaller than n. We're going to change it and see what happens and if it's going to be successful or not if we make m too big. So right now, phi n equals 20, p equals 3, q equals 11, phi n equals 20, n equals 33. And then m is 32 right now. Let's make it small, like 13. And then, so these are the different variables that we know already. And then this is c equals m to the power of e mod n, which is the ciphertext. And then m found equals c to the power of d mod n, which is the plaintext found again. So here we're basically doing the function but not using the function. We copied it down here because we know n already. Same for decryption. We use this line over here to decrypt it to get m found. So afterwards we print original plaintext and then the value of m, and then decrypted plaintext and then the value of m found. If m is the same as m found, then the decryption is successful, else it's an error. Okay, so now we're gonna try with m equals 13. So 13 works, and let's make it bigger. $18 also works. $23 works too. $28 also works. And then the next one is 33. So if we do 33, m is the same as n. What will happen? The decrypted plaintext becomes 0 and it turns into an error. So we know that when m equals n, it doesn't work. Let's see if when m is bigger than n. When m is bigger than n, it also doesn't work. It used to be 38, now they find 5. So we know that as long as m is less than n, like 32, it would always work. So in conclusion, only m is less than n works. That is like experimenting for one of the restrictions. Okay, next, for public key E is a whole number between 1 and phi n, and E is coprime with phi n. For this restriction, a topic that we're going to cover in the future is determining coprime to find public key E. And we're gonna input two numbers and see if they have any common factors in the future. Private key D has two restrictions. D is greater than 0, and D times E divided by phi n has a remainder of 1. So the topics here are Euler's totient function. So why does phi n equal p minus 1 times q minus 1? And the Diophantine equation to find the private key D. So we know that D times E divided by phi n has a remainder of 1, and the Diophantine equation can help us find D. So here are the topics for the future. In meeting 10, we're going to do prime factorization, finding P and Q. Number 11, determining coprime to find the public key E. Number 12 is Euler's totient function. Number 13 is extended Euclidean algorithm, or the Diophantine equation, to find the private key D. And for the number 14th meeting, we're going to do the full code with the public and private keys. Also, we're going to find the digital signature and digital certificate on the computer, which is not part of the code. So onto the part of encrypting and decrypting RSA on text documents. The process is like this. Alice starts with a plaintext in plaintext_rsa.txt. She finds the ciphertext and she sends the ciphertext to Bob in ciphertext_rsa.txt. Bob receives ciphertext and recreates plaintext in plaintextfound_rsa.txt. Now let's look at the code. I'm gonna run it first so I can compare the results with the code. Okay. So from the top, we have the two functions again. Encryption, which returns the ciphertext using P, Q, E, and M, and decryption, which returns the plaintext using P, Q, D, and C. So we can use these two functions when we're encrypting or decrypting. Here, this is the same thing as last meeting's code, so we're just using it to test the two functions and to define some of the variables here. The restraints are the same as before. D is greater than 0, P times Q is greater than M, and greater than C. E and phi P times Q are coprime. So here, M equals 3200. This is the message that we're going to encrypt. And then we print plaintext, value of M. P is 53, Q is 61. Phi is P minus 1 times Q minus 1. And then print P times Q. And then print phi and the value of phi. So for these three, we can see in the results that the first print, it prints plaintext and then 3200, which is M. Here, the next print says P times Q. So this is the value of N, which is 3233. And then we print phi and the value of phi, which is 3120, by calculating P minus 1 times Q minus 1 here. And then we give the variable E value 17 and D 2753. And then we print E times D mod phi. This should equal 1 because it is one of the restrictions. And it does equal 1 here. So we know it's going well so far. And then encryption P, Q, E, M. So we encrypt message M with P, Q, and E and give the ciphertext to C. And we print pow ME and the value of M to the power of E, C equals, and then the value of C. So this is the value of M to the power of E. It's a really big number, and we don't really need to use it right now. And then C is the ciphertext, which is 1380. So that's the ciphertext. And then if M is the same as M found, then we print the value of M and the string process successful. Oh, wait, I skipped one. So after we print that, we find the plaintext again by decrypting the ciphertext C with P, Q, and D. So we find the plaintext and give it to the variable M found. Then we print pow CD, the C to the power of D, and then M found, and the value of M found, which is the plaintext. So here, the C to the power of D is really big, so it's very big. And then M found is 3200. So it's the same as before, and it's gonna print process successful over here. If it isn't the same, then it would print the value of m and incorrect. Here we printed a empty thing, so it skipped a line here. So after we tested it, we can know that this part and the functions are all working well. So we can start doing the encrypting and decrypting the text files. So now we're going to do encryption on text file plaintext rsa.txt. This file, so the name is plaintext rsa.txt. We open it in read mode, so we can see in the folder here that I have the plaintext rsa.txt here, and I have this paragraph in it that I'm gonna encrypt. And then right now these two, I don't need them because we're gonna create them again. So the code is gonna read this document. It opens plaintext rsa.txt in read mode, and then it reads it and then gives all of the things in the document to the variable ptxt, and then we give ptxt to character string. So right now character string contains the message that I want to encrypt, and then we have a new string which is an empty string. And then for the loop, for character in character string, m is the character's ord. So ord is the ASCII number for the character, and every character has a ASCII, which is also Unicode. So we basically turned the character into a number, and we give that number to m. And then we encrypt m using the encryption function and p, q, and e, which is the public key. After we encrypt it, it will still be a number because we encrypted a number. So we want to turn it into a string, and so this is why we put a string in front of it. And then we give the string to new character, and then we give the new character to new string. New string is at the beginning, it's empty, but then it gets filled with a new encrypted character each time. Also, every time we add new character, we add a comma in it, because we know that the encrypted each character has 4 digits. So we want to know what, we want to separate the different digits of different characters. So we put a comma to separate different characters. Because we put a comma on after every single 4 characters, we want to take off the last comma because it affects the decrypting process. So before we take off the comma, we printed new string. New string is a set of numbers which are all around 4 digits and separated by a comma. And then we strip the new string, and so we take off the last comma of new string and then give it to trimmed, and then we print trimmed and the value of trimmed. So over here, this is the end of new string, and we can see that it has a comma at the end, but for the trimmed string, it doesn't have a comma after 2825, which is so this comma disappeared. And then we give trimmed to new string and change the new string from having a comma at the end to not having one, and then we print an empty line here. And then we close the document of plaintext rsa.txt. After we found the encrypted message, we're gonna create a file to put the ciphertext. So the name of the file is ciphertext rsa.txt. We open the file in write mode. When Python tries to open the file and realize that it's not there, it's gonna create the file, So after we run it now, I used to not have a file called ciphertext rsa.txt in the folder, but now, oh, I think I deleted it. So I'm gonna run it again. So now it has the ciphertext rsa.txt in it, and in it has the ciphertext, which is presently a bunch of numbers separated by comma. So this is the ciphertext that gets sent from one person to the other. Okay. And then we put the new string in it, which is what we just saw, and close the document. After that, it prints RSA ciphertext file was created. Here. And then we're going to decrypt ciphertext rsa.txt. So we open it in read mode, read it, and give all of the message into character string, and then character string equals ptxt.split, comma. So we're going to split the message at every single comma and put it into character string. So now character string is going to be a list with a bunch of elements in it, and each element is a number which corresponds to a letter when we decrypt it. And then we print character string, which is the squeeze text over here. So we can see that it's a list, and elements are the numbers that were encrypted from before. So now we're going to decrypt this list. We have an empty string, new string, and for I in range, length character string. So length character string is seeing how long the character string is, so how many elements are in there basically. And then because the amount of elements are the amount of letters in the message, so we want this for loop to repeat that many times. And then inside the loop, character equals character string I. So the first time it will be character string 0. It will give the 0th element to character string, which is the very first element. And then we're going to find the integer of character string, because we know that in the list it was all strings. We want to turn it into an integer. And then, so C is an integer of the ciphertext, of one of the letters or the elements in the ciphertext. And then we're going to decrypt C using the function decryption. And then because after we decrypt it, it's going to turn into M, which is the plain text, but M is still a number. We want to find the character that the number corresponds to, so we use char. This is like the function for ASCII, turning a number into the corresponding character. And then we give that character to new char, new character. And then after we found the plain text character, we add that to new string. New string just gets new characters added in every single loop. After the loop, all of the characters, all of the numbers have turned into the characters from the plain set and plain text, and the plain text is contained in new string. So we're going to print new string, and we can see that this is the original plain text, and it looks pretty successful. And then it prints an empty line and closes the document. Lastly, we have the plaintext. We're going to put it into plaintext found rsa.txt. So we open the file in write mode. Again, it wasn't there before, so they created it. And then we write new string into it and close the document. So we can see in the plaintext found rsa.txt, it has the plaintext from before. If we compare it, it is the exact same thing as plaintext rsa.txt. And then it prints plaintext RSA file was created, which is here. So now we have successfully encrypted a text file using RSA. Thank you. Q. Q. Q.